Hello, I'm Mr. O'Rourke, and this is a lesson on Continental Drift, Alfred Wegener, and seafloor spreading. Alfred Wegener was a meteorologist, a German meteorologist that lived from about 1880 to about 1930. He was a meteorologist by trade, but he also had interest in geology and paleontology. One time when he was looking at some fossils, he noticed that the same fossil was on two different continents separated by an ocean. And that got him to thinking, well, how does this happen? Darwin's theory of evolution was widely accepted by then, and he knew that they couldn't evolve on two separate continents separately. So he started looking for evidence of what could cause this. It brought him to think of the theory of continental drift, or the idea of continental drift, his hypothesis. He started gathering evidence that the continents were together and had drifted apart to their current locations, inspired by these fossils. He thought that all the continents were joined in one single landmass, which he called Pangea, but means all lands. They were all together at one point. Now, in order to find evidence to back this up, he started with landforms. By looking at the fit of the continents, how they fit like a puzzle, kind of gives evidence that yes, they were there. Now, if there were mountains here and plains here, that wouldn't make sense. Okay, it's not, they wouldn't match up. But if there were mountains here and mountains there and plains here, plains there, if the landforms matched up where the continents connected, that would lend evidence that they actually were the same landmass. So when Wegener started looking for that, he started looking at mountains, like the Appalachian Mountains here, okay, up through North America, and then up in England and through Scandinavia. He started looking at them, and when he put the map together, he noticed that they started sliding in together, that they matched up. They formed one continuous landmass, or a mountain range through here during here. They looked at South America and Africa. Everything seemed to line up. The next piece of evidence that he looked at was fossils. This was the one that got him started in the first place. So he started looking at fossils. Find it? Can't find it. All right, so when he looked at the different fossils, he would look at where were the fossils found, these ancient fossils, and he found that they were separate, that when he put the puzzle together, the territories overlapped. Okay, this was more than a coincidence to Alfred Wegener, and he surmised that the continents must have been together. You have these land animals that couldn't cross an ocean. Mesosaurus could not cross a salty ocean. It was a freshwater reptile, could not have crossed the ocean. We have Lystrosaurus, which is found in Antarctica, India, and Africa, but only in this band. Okay, this is where it moved. It's not like it was found in Antarctica and then up here in Africa, totally separate. They've had these paths which they were found. This is from a plant, a fossil of a fern-like plant that goes through here. All this evidence seems to show the fit of the continents, the landforms match, the fossils match across. It kind of shows that the continents were once together. The last piece of evidence that Wegener used was climate data. Now, he found that there was evidence that there was glaciers in South Africa and in India, South America. Deep scratches in the land there showed that there was glaciers. Being close to Antarctica, down by the South Pole, they would have had glaciers there. Where they are now, they could never have glaciers. Wegener surmised that they must have been closer to the South Pole and drifted north. Also, there's islands like Spitsbergen that's in the Arctic Circle up north and has evidence of fossilized tropical plants. He theorized that that island was much closer to the equator and had drifted north. It seemed that all the continents had drifted a little bit north from where they were and kind of fanned out from there. I have a little video here that kind of shows how they kind of moved out from their current position. So we can see, moving down, you can see India over here, Africa, South America. So this is what Wegener kind of thought happened. Now we have India moving into Asia, Australia moving out this way. We have the Himalaya Mountains up here, different parts opening up. Pretty interesting. That was the thought behind Pangaea. Now, in 1930, on an expedition to Greenland to find evidence for continental drift, Alfred Wegener died on the expedition. He froze to death. He got lost out there. His ideas kind of were put on the shelf. Not many scientists thought they were very credible. They thought it was too fantastic that these huge continents were moving. What could move a continent? There must have been some other explanation. For all his other evidence, there's probably other little things that they haven't discovered yet, and they'd find out and it would be explained. So for a while, it sat on the shelf until World War II started. Once World War II started, Harry Hess was a geologist at Princeton University who was also in the Navy Reserve. He was called up once World War II started, and in his ship had sonar for trying to find submarines. Being a scientist, he left it on all the time and was mapping the ocean floor. You could also get the depth of the ocean from the sonar at the time. At that time, the idea was that the Earth was made in one shot. It cooled, and you had everything the way it is back at the moment it cooled, and that nothing was changing. The bottom of the ocean was like a bathtub. It was flat. They didn't believe any real life existed more than 50 or 60 feet down. Once there was no more light, there was no way life could exist down there and everything. When Harry started going through, he found that there was a mountain range in the middle of the ocean that stretched through all the world's oceans, and it was really curious. After World War II, they started investigating it, sending submersibles down there with cameras to look around to see what was down there. And they found on this mid-ocean ridge, there was a lot of life down there. It was teeming with life. There was all kinds of tube worms and crabs and octopi. Lots of life down there, and it was warm. Okay? They also saw molten material erupting from this mid-ocean ridge. Now, that was the first sign, okay, that things were changing. That they could see that this molten material was erupting, and it was making these pillow-like shapes. Okay, these pillow-like shapes, call it pillow lava. They call it pillow lava because as it comes out and it cools in these tubes, kind of like shapes. Again, they break out and they come over here. Now this pillow lava is found all over the ocean floor, all over the place, but the only place it forms is by the mid-ocean ridge. The only way it could get all over the ocean floor is if it forms at the mid-ocean ridge and that crust is pushed away and takes that pillow lava with it. Okay? The fact that it's all over the ocean floor shows that the ocean floor isn't static, that it's moving. It was a good piece of evidence. The second piece of evidence that the ocean floor isn't static and unchanging is the magnetic striping of the ocean floor. Now, basalt has a lot of iron in it. Iron is magnetic. Whichever way the Earth's magnetic pole is facing, like it's facing north now, the rocks that form, the igneous rocks that form then, with the molten rock in it at the time, will all follow that magnetic field and point north. When it hardens, it's stuck that way. The magnetic pole shifts like it does every few 100,000 years, and the magnetic pole points south. Those rocks will still point north. But the newer rock that's made, their magnetic particles point south. When it cools, they're stuck south. They won't turn, they can't turn again, and so on and so on. So, by finding these alternate bands of magnetism across the ocean floor, which is another way they were trying to detect subs through magnetism and things like that, they found that the ocean floor had magnetic facing north, facing south. If they're a mile or so facing north, again, the only way they can explain this is if molten material is coming up and kind of pushing out to the side and is creating over years. Now, when we think about how the idea was before Wegener, was that it was all formed at one time. If the ocean floor was formed at one time, it would only have magnetism in one direction. Because it has it in alternating directions means that we live on a dynamic planet where the ocean floor is spreading apart and pushing the older material out to the sides. Now, in order to confirm this, scientists started looking at rock samples from the oil companies. And where are they drilling? Where are they taking it out from? And what they found was that the further you get away from the mid-ocean ridge, the older the rocks were. The closer you get to the mid-ocean ridge, the younger the rocks were. This was the final piece of evidence that they needed that showed that Wegener was right. The continents do move. And seafloor spreading, okay, the molten material coming up, pushing out to the side, is the mechanism for how it moves. And that was strong enough to move the continents. This brings us to the theory of plate tectonics. My next video, I'm going to get into the actual theory of plate tectonics, how this is all tied in together, and what are the forces in the earth that drives the plates, which makes them move around, and how that allows us to predict earthquakes, volcanoes, and how it even influences the rock cycle and everything else that we do in geology today. So, thanks for watching. See you next time.